Well, good morning and welcome to this Friday's Cosmic Conversation. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences. And today I'm delighted to have with us Dr. Kim Arcand, who's the visualization scientist at the Chandra X-ray Observatory. Welcome, Kim.
Hello, how are you?
Pretty good. It's been a long week, but you know.
Yes, it has.
They're all long, it seems like.
Yes.
So actually, maybe as a first question, can I ask about your title? Like, what is a visualization scientist?
Yeah, it sounds a little pompous maybe, but you know, I like to think of it as I get to be a storyteller, or I get to sort of play in this universe-sized sandbox of data. Essentially, my job is to just take that information and transform it into something else, whether it's an image or a model or a sound. It's a pretty fun job to have, though. It is.
It's a pretty expansive definition of visualization too, that it's becomes, as we're going to talk about, something we can hear, not just see, but hear, and something that's tactile. And I think that's really kind of amazing, particularly when, like, Chandra, because it's an X-ray observatory and isn't quite as like intuitive in certain ways as like a Hubble image, and that it's really kind of cool to see how you've expanded these ideas of how to communicate the results.
Yeah, exactly. We can't naturally see X-ray data out in the universe, right? We have to be able to translate into something. So we don't have to just privilege sight when we're doing that. We can sort of use other senses to be able to explore it in new and different ways. And I think that's really fun. It really is. It's like a sandbox I get to play in all day.
Very cool.
It's great.
What brought you to Chandra, or how did you get into the
you know, my background's a little strange. I actually started in biology. I was studying molecular biology specifically as an undergrad, and kind of realized I didn't want to spend my life looking through a microscope. So I went all the way to looking through a telescope, except virtually, because you never actually look through the Chandra telescope.
Right.
But really that sort of in between, the connection point between the micro and the macro was just computer science. I loved computers. I loved working with data. I loved getting to be able to like translate something from one form to another or transform it.
Yeah.
And yeah, computer science was just that nice connective tissue.
It's really interesting. And actually, I mean, the microscopic realm is also this invisible realm. And so you still have to have that same kind of visualization.
100%. And honestly, I think the two fields could learn a lot from each other, really, because there's a lot of similar procedures and mechanisms that are used in both fields for different outputs, perhaps, but still, there's a lot of synergies there.
Very interesting. Well, I guess in the interest of kind of getting to some of these awesome visualizations, you were going to share a little bit about the background on Chandra with us, I think.
I am indeed. So yeah, let's bring this up. So I'm going to just sort of step you through some of my favorite visuals and do a quick tour of some of Chandra's greatest hits, if you will. NASA's Chandra X-ray Observatory is this really cutting edge piece of equipment still to this day. It's over 20 years since Chandra was launched. So it's been quite literally decades since Chandra has been planned and built and launched and then finally operated for almost 22 years at this point. So Chandra is a space-based telescope. It's one of NASA's great observatories. It's like a sister telescope to the Hubble Space Telescope. And essentially it goes a third of the way to the moon at its farthest point from Earth. So it has this really lovely sort of upper view of the X-ray universe and has very efficient observing time to be able to stare out into that dark void and capture all of those little bits of X-ray goodness, all those photons, those little packets of energy. And then we get a lot of data to be able to take and do something with. So the type of science that Chandra gets to study includes so many things, from exploding stars, from areas around black holes, from colliding galaxies, and much, much more. Though there are not as many X-ray photons out there in the universe as there are optical, there's still an amazing array of different kinds of celestial phenomena to be able to understand.
Well, these are like the highest energy, aside from gamma rays, like the highest energy photons too. So we're really looking at just some crazy energetic phenomena.
Yes, right. We don't get to play the Hulk thing with the gamma rays, but we're right down. We're one next step down, which I think is pretty cool. Oh, sorry, pretty hot. It's definitely a very interesting area to be working in because, you know, this is this is like a compressed amount of time that humans have been able to study the X-ray universe. It really wasn't until the 60s. And even then, like more advanced telescopes didn't come along until later. So, and Chandra is one of the most advanced of them all still to this day. So there's a lot that we've been able to learn about the high energy universe in a pretty small amount of time, you know, when you think of how long humans have been around.
Compared to the hundreds of years that we've been using telescopes.
Exactly. I think we're doing a pretty good job. So yeah, so we have all this data. Oh, sure, go ahead.
We had a question here about whether Chandra was meant to last that long. Was it a 20-year plan, or has it exceeded the?
So yes and no. Officially, it was a 5-year plan because we wanted to hit that 5-year mark and have all of that success that would bring. And you know, Chandra did answer its sort of basic questions pretty early on in the universe, like what is the X-ray background and what are these exploding stars and what are all of these different kinds of high energy lights. But really, when the telescope was being planned and built, the hope was. And I think the former director, Harvey Tannenbaum, put it this way, that it took about 23 years, I think, to plan and build. So the hope was that it would at least last 23 years in operations, and of course, well beyond. Because, you know, I will say, you can get very attached to these missions. You know, their Twitter accounts might have a little personalization for fun, but in all actuality, when you're working on a mission, you do get very attached to them, and you tend to like almost attach a personality to them. The success of the science, it's so exciting. So you never want to lose this tool, this very unique tool that we've had the privilege to work with.
And the spacecraft can have problems and things that need to get fixed. And it's almost like you're doing long distance, like engineering and medical care for these. These really,
yes. It's like the way we take Chandra to the doctor is essentially just uploading code, right? It goes so far, we can never visit it in person. So we are just uploading code, and the engineers and all the folks in the operations groups, the mission control and all of that just do a fantastic job to keep Chandra up and running in that harsh environment of space. Yeah. So I can start showing you maybe some of my favorite images. We're just going to be looking at a lot of multi-wavelength imagery, which does happen to be among my favorite. I think these days astronomy is such a multi-wavelength field. All of these different kinds of light, and then even things that are not kinds of light, are different tools in the astronomer's toolkit, right? And so you kind of pull out the right tool that you need for the job. So whether you're studying something like a stellar nursery or an exploding star or some of the largest structures in the universe, you know, you have these questions and you have to figure out which is the right tool to be able to use to understand it better. So, Chandra is very sort of complementary with these other forms of light, and a lot of Hubble data we'll see in the following few images as well. Hubble being such an iconic telescope, of course, but other kinds as well, such as infrared and radio. X-ray play very well with radio, which are the opposite sides of the spectrum. They're very, very complementary. So
how that works,
it is so interesting. They're like BFFs, even though they're very far away from each other. So the Eagle Nebula is probably one of my favorite images. It's incredibly iconic, and Chandra was able to add to that sort of playing field of data. We've got all sorts of stellar nurseries that Chandra's looked at, more mature stars that could go exploding anytime, stars that have already exploded and are moving on to their next phase of transformation, things like pulsars, galaxies of all shapes and sizes, like rings, like whirlpools, things that have a beating, pulsing black hole heart at their center. And then, of course, some of the largest structures that are gravitationally bound in the universe, clusters of galaxies where all of these really big chunks of X-ray hot gas are and even things that look like they're smiling back at us. It's, you know, it's Friday. I feel like we could all use a cosmic smile thanks to gravitational lensing. So those are just a few of some of my favorite images. And it's really been a pleasure to work on Chandra for the past, I don't even know how long I've been here, 23 years, because, you know, you get such exciting data to be able to work with. So the way that the data processing pipeline works, there's this object out there in the universe, Chandra's directed towards it. You know, it's scheduled into Chandra's like diary, if you will, and it's capturing all that information that has been traveling from that celestial object for however many many, many years. And then it's recorded on Chandra's detectors and scientific instruments, packaged up in the form of ones and zeros, and sent through NASA's Deep Space Network before eventually it makes its way somewhere in Massachusetts or anywhere really in the world that it can go. So really it's all data. And Ryan, you might remember this slide because I know you've presented a similar slide, which I borrowed for a while and then replaced. This is actual bit of binary code from one of our Cassiopeia A observations. So all of these ones and zeros, it's all the real deal. Of course, there are many, many more lines in the actual data set. Exactly. But we get this fantastic table of data to work with, right? So the time, the location, and the X and Y coordinates, the energy, all that information that was recorded during the observations. You just start with something that perhaps doesn't look super exciting, but is really information rich. And then you start working with it to translate into something else. The scientists are going to be working on it to analyze it for their data. They're going to be using like this spectral information, that sort of DNA or like fingerprint of light, to be able to understand the processes that are happening. And then, of course, when it gets ready to make something, for example, a non-expert audience, we're going to process it to be able to look like the object and the science that we need to be able to describe. So this image, Cassiopeia A, was Chandra's first light. It was essentially the official first image that we released from Chandra to show that it was working. It is a supernova, an exploded star that's a little over 10,000 light years away, where a light year is a distance that light travels in a year, about 10 trillion kilometers. And this was only about an hour's worth of observational time. And you can probably see at the very central region of this remnant, there's a very bright source. And that is that compact source, that leftover core from the star after it exploded. And that hadn't been directly seen like this before. So within the first hour of Chandra's first light observation, there was fantastic science already on display.
Not bad for an hour's worth of work.
Not bad, right? And we're just transforming this image slowly now to a more modern version of it. So fast forward 20 years, and Chandra has looked at Cassiopeia A many, many times since then. It's a calibration target, so it's actually used to kind of help make sure everything is on track. And it's also a very famous object in the night sky as well, with a lot of sort of sciencey goodness in there still to discover. So now we're looking at like over about 1 million seconds worth of data. And what we've done here is sort of the image so that we are using that spectral information, that fingerprint of the light, identifying it and then color coding it like you would color code a weather map, a temperature map on the nightly news, or a wind speed map or what have you. Except now we're looking at the silicon, the sulfur, the calcium, the iron as it's dispersed through this remnant, all of the debris left over from that explosion.
So basically translating the color of the light, which is at that specific frequency, to knowing what element is creating that.
Exactly. Yeah, so it's a great little, cosmic treasure hunt where you can see the iron, for example, is that purple color. So you can see that it's a little bit more heavily situated around the perimeter of the remnant. And what's interesting about a supernova remnant like Cassiopeia A is, so as the star is aging, it's running out of fuel. These heavy elements are building up in its core. And right before it explodes, the iron is at the core of the star, right? And it's too heavy. It's not got enough fuel, it collapses, and then it explodes all over the place. So what was at the innermost core of the star is now all along the perimeter pretty heavily. So it's a lovely visual example of that process, that when a star like Cassiopeia A explodes, it essentially turns itself inside out. And this is just a nice visualization of seeing those stellar guts that have been, turned inside out and spread all the way out. So yeah, it's a pretty exciting object to be able to work on. And again, since we have so much data, we've been able to look at it over time and then also look at it in 3 dimensions. And this 3D model is a really fantastic example of what happens when you have a really good little treasure chest of information. We worked with Tracy Delaney, who was a scientist at MIT at the time, to be able to create a visualization of this model transformed into a 3D space so that, we're all here on Earth, right? We're not leaving anytime soon for the most part, most of us at least. So the universe is almost like a TV screen to us at times, this sort of 2D seeming view.
Right.
And having the ability to understand what of the information is moving away from us and which of the information is moving towards us is actually a really useful tool. The scientific research of having a 3D model like this is helpful because it helped show, for example, that this explosion occurred in two pieces, the spherical shell and then those really strong jets that came out at opposing angles and surpassed the speed of the shell. And then, of course, like I was just mentioning, it's also a nice visual way to understand how the material, the various bits and pieces of it, the silicon, the calcium, the iron, what have you, how it dispersed from that initial star through the explosion and out as it's being disseminated throughout the universe.
Well, so we actually have a 3D representation of our galaxy that we can share. And just as a little bit of a plug, some of you are probably watching this on the OpenSpace YouTube channel. OpenSpace is a open source software platform that you can download yourself and tinker with. We're going to show some things that aren't in the sort of official build yet. They're still kind of on the more experimental fringes. But one thing that is available in the software is being able to find locations of pulsars. And now like Cassiopeia that we were talking about is a supernova remnant, as are these little red dots that I'm kind of highlighting. These are the locations of, like you pointed out, that kind of bright core that Chandra observed for the first time in Cassiopeia. These are the sort of remnant neutron stars that are pulsing rapidly and actually observed first in radio, these incredibly energetic.
That's right.
So again, showing that
radio rocks. It does. Yes.
relationship.
Exactly.
Yeah, but we can target Cassiopeia and maybe look at another sort of a 3D model that you were mentioning. Oh, and actually,
let's zoom on in.
Go ahead and let me just get rid of our little red markers here, but just to get a sense of that there are many of these objects, these pulsars out in the galaxy. It's just that we're going to zero in on a few kind of these rock star supernova remnants that have been observed really well.
Yeah, scientists estimate we have a new supernova going off about every 50 years or so. So over time, you can build up quite the collection of supernova remnants to study in a galaxy like ours, which is exciting. There's a lot of different objects nearby, 10,000 light years away, or 11,000 years to be specific for Cassiopeia. It's really not that far, right? We've got a great view of it.
In the scheme of things.
In the scheme of things, cosmically speaking.
Traveling there anytime soon, but still
no.
Exciting.
Yep.
So this, I guess, is sort of like the next generation model of what you were showing earlier?
Yes, exactly. This is an updated model from Sal Orlando in Italy, and it's showing again the mapping. In this case, there's also simulation data that's been added in, but it's heavily observational data as well. So it's a little bit of a combination. But you're seeing again the iron in this case is now colored green. So you're seeing that it's dispersed along the perimeter. You're seeing in this version, it's a nice like hollow kind of shell. This is a really low density of material, anywhere from 10 to 100 bits of these little particles per cubic centimeter. So this is gas, and again, by color coding it, you're just able to understand like where the silicon is and the argon and the neon and the iron, as I already mentioned, the cooler material that's towards the center and the hotter material that's towards the perimeter. It's just a great way to be able to visualize all of that chemical, bits and pieces of it.
It's kind of interesting too that it's almost like a medical, like a CT scan or something, where you can kind of start to see in 3 dimensions.
Well, so there's a little story about that. The very first version that we worked with Tracy Delaney on for this model was actually built using medical software that had been borrowed from some local Boston area hospitals. Alyssa Goodman's team, she's at the Center for Astrophysics as well, had been working on some molecular clouds. They worked with some brain imaging scientists and adopted software that's used for MRIs essentially to be able to work on astronomical data. This is going back to like 2008, I think. So we now have new and different software to be able to use in astronomy for 3D, but at the time we really didn't. And this was groundbreaking. It was the very first time we had actual observational data from NASA and other telescopes modeled into 3 dimensions of a supernova remnant. And it kind of changed my world. It definitely offered me a very new perspective, quite literally, on the universe and on what we could do with it.
Well, then, now I don't know if it's this one that you have an example of, but then you've also taken these 3D models and made tactile versions, correct?
Yes. So some friends of mine that work at the Smithsonian were in the process of 3D scanning President Obama's head and turning it into a 3D printed bust. And I was like, well, if they could do that with Secret Service all over, I'm sure we could figure out how to 3D print Cassiopeia A. And so they did. They helped us work with our very first STL file to be able to turn it into a 3D print. So I don't know if you can see my camera, but I'm holding up one of our early models. And we actually worked with some students at the National Federation of the Blind to take these 3D prints and improve them so that someone who is either blind or low vision would have really good access to this data in a very unique and new way. And yeah, that was one of the most gratifying projects I think I've ever worked on. So.
And what was that made out of? Was it a plastic 3D print, or was it?
Yeah, this is plastic. It's a PLA filament. My dog is barking in the background, of course. Hopefully you cannot hear Juno. Anyways, this is a plastic PLA filament. This is about 8 inches across, and obviously it's hard plastic, whereas the real object is very gaseous, of course, and also about 40 million billion times the surface area of our sun and planets. And if you're a Pluto lover, toss Pluto into that math. It makes no difference. It's very massive. So quite different. But the 3D print, it really does. One of the things we worked on with the students were improving the resolution. So the tactile quality was really strong, cutting it in half. So you had access to that internal shell versus just the external information, doing things like making the jets attached by magnets so that it would be easier to work with. So many great things came out of that. Yeah.
Well, we have a couple other examples. Which one would you like to visit next?
Let's see. I guess we could go to the Crab. That is not too far away from Earth. That's only about 6,500 light years away. So also in the Milky Way.
Right. Give a little context before we go to the 3D model. Maybe we can show the picture that we have of the Crab. So this is, if you were to, well, you should talk about this image.
Sure. So this is, the Crab Nebula in 3 different kinds of light. Again, I think it's so useful to have all different kinds of light when you're studying these objects. And in this case, we're looking at the purple data is the X-ray information from Chandra. The red is the infrared information from the Spitzer Space Telescope. And the gold is the optical data from Hubble. And you can see how the high energy heart is really situated in the nested structure at the center. And it's got a very strong disk and some jets. And then the cooler material from Spitzer and Hubble is much larger. So the Chandra data is maybe 40% smaller than the infrared data. And great observations also from this of this object from radio telescopes as well. There's lots of really good multi-wavelength data of the Crab. So I think we're going to explore it in 3D now. Right.
And this is helpful to see that other image first, because in 3D, this is you kind of zeroed in on a particular part of it.
100%. This 3D visualization is from Frank Summers and a team of us from the Universe of Learning. In this case, we have a 3D model of just that inner sort of heart, the high energy heart of the Crab at the very innermost region. If you could get rid of the disk for a second, buried inside that disk, right at the central region, is the pulsar. So that map of pulsars that we were looking at earlier, this would be one of those little tiny red dots. And now we're getting a much more up close and personal view. So it's this really dense core of the star left over from the explosion. And it's spinning around really, really fast. And so there's this superheated disk that's going around it, as well as those sort of bipolar jets that are shooting out either side. And all of that, again, sits into that larger, cooler nebula of gas and dust that we saw in the two-dimensional image. So again, we have the 3D prints of this to be able to hold a pulsar in your hand. Oh, and this matches my sweater. I'm just realizing, very nice. It's a great way to be able to talk about scale. This is the disk is maybe what, a light year across, perhaps. I'd have to check that, but approximately 10 trillion miles across, and we're able to hold a very plastic, compact version in our hands.
Well, it's also interesting because it's really because all of this is in motion, that we're able to do a 3D reconstruction, right? It's being able to measure that, like where this gas is moving, that we can actually sort of recreate this 3D. So it's kind of an interesting contrast too to the static thing that it's actually moving rapidly and expanding.
Yes. And I think one of the things that is hard to get across, and I see a great question that just popped up, is it still actively spinning? Yes. So, if we're looking at this in a still form, just in OpenSpace or just in my plastic print, it doesn't give the sense of that dynamic change. But there are some fantastic, I should have thought to show them, there are some fantastic time-lapse movies that we've been able to put together from the data that show chunks of this object changing over time. So just like Cassiopeia A, Chandra's been watching Crab for a long time, and we can actually still see. I wish I had the time lapse. We can see those particles as they're sort of wishing out across the disk as a result of the spinning, the very high speed of that pulsar buried inside, and it's quite powerful, I think, to be able to see data changing over time in that way. It just brings home that point that the universe around us is ever changing and ever moving, and we're a part of it.
Absolutely. And we can actually, we'll go back and we can put a link into the comments on both YouTube and Facebook so that we can go back later and you can see some of those movies, because I think it's just cool that we're like making movies of these amazing objects. Yeah,
that would be great.
Yeah. And then I think we have one more that we can show. Maybe we'll start with the still image of the Tico.
Yeah. I call it Tycho. You say potato. I say potato. I don't know, whatever. But yeah, so this one is another very lovely supernova remnant from the Chandra Observatory. This one is about 13,000 light years away, if I'm recalling. And again, it's an observation that, or target rather, that Chandra has been able to return to over and over because we have a great view of it. It's very X-ray bright. As you can see, this is almost all X-ray data that we're looking at here, with just an optical sort of star field behind it to set the context. Because one of the things we learned very early on is these objects can look so different in X-ray light, blobby, some might say, or clumpy or lumpy. I'm in love with them still, but maybe, beauty is in the eye of the beholder. But when you situate it in context, when you're able to, add a little optical data, it really does help immediately situate you in sort of the right framework that, we're actually looking at something from space and not something under a microscope.
Well, it's interesting too, because there's a challenge with OpenSpace, for example, because we use an actual star catalog, and that catalog kind of peters out by the time we're off in this direction. And so we don't have many stars around it. So when we switch to our 3D view of this object, you'll see we don't have many stars in the background just because they're, in terms of the 3D positioning of stars, now with Gaia, all of this has changed, but we don't really have that in the data set right now. So it is a little bit of a kind of isolated orb in space here. But
yes, it is, but that's okay. There is a lot of space in outer space, so I think that's fine. But I think what I liked about the data set and even the 2D image that we had showing before, it's actually color-coded by dimensionality, if you will. So the blue information is the blue shifted material moving towards us, and the red information is the red shifted information moving away from us. And we worked with Sato, Dr. Sato, on this project as well to be able to visualize that dimensionality of it in the 2D data for the first time. But then we also have the 3D model that you have up, and this was from Giles Ferrand and his team. I believe they're out of Japan. They have this wonderful three-dimensional model. It's, again, a simulation that's been constrained by the X-ray observations. And you can see here that Ejecta is part of this object. That's that shell in like the pinkish color along the outside. And then inside you've got all of the ejecta. So those little clumps of gas, that the debris that's left over from the explosion. And you can see, as Ryan's kind of going in and out of transparency, that it is a sort of hollow-like shell. These are not compact themselves. These are expanding shells. And Tycho is a great object as well. It's a different kind of supernova than Cassiopeia A, for example. It is a type 1 supernova, so there was a companion star involved in that explosion, and the thermonuclear reaction of pulling all of that material off and eventually just getting too fat. So it really is a fantastic object to be able to study, because you can really see such differences looking at them. This sort of clumpy texture versus the lumpier texture of Cassiopeia A that we were experiencing earlier. These are great objects to study because it's like a standard candle in the universe, and very, very helpful for research. So yeah, I have a 3D print of this object as well. I don't know. Oh, it's green, so you can't see it. Oh, how funny. And why do I have that weird background? Anyways, I wish you could see it, but it looks like I'm holding a piece of the universe in my hand, which is pretty funny. So anyways, I'm holding a very cool version of it in my hand. You just can't see it. And once you have these 3D models, it's not just to have in one format. We do a lot with them. We bring them into virtual reality, for example. And like the first time I ever walked inside a dead star that I had been staring at like my whole career, it was really exciting. Like it transforms you when you can walk inside it and experience it so well. Yeah, let's do that. I mean, does that not feel like you're going inside some sort of like molecular thing though, right there?
Yeah. It does. It looks like some kind of cellular life form.
Yeah, it really does. It really does. But I think it's a really fascinating way to be able to explore a universe. It has absolute scientific interest, but really I love it for the sort of ways of communicating, the different ways that we can communicate data once we've been sort of freed up from just a 2D space. It's very exciting. There's just a lot of potential.
Well, before we go, it would be great to talk about one other project, which is not just using 3D and visual tactile experience, but also sound.
Yeah. This is a personal favorite of mine these days. We had started working on some data sonification, this idea of translating information to sound, pre-pandemic, and attaching it to that 3D geospatial sort of object, right? But then the pandemic hit and we couldn't get in our lab and students had to go home. And so instead we started working on the transform into sound. And we worked with Matt Russo and his team as part of System Sounds to take it and translate it into a way that would really make sense for the science, this high energy goodness, so to speak. And Cassiopeia A, one of the first objects that we translated into sound. You'll notice that there are different angles of sound that you're going to hear. You're going to sort of see the remnant as it's expanding, and the movement is kind of helped dynamic objects. There is a different synthesized sound for each of the different layers. So the iron, the silicon, the calcium, the sulfur, and you'll hear all of that composited together. Why don't we hear what it sounds like? Yeah, so it's tracing all of those high energy knots and structures as you're expanding through the remnant. It was a true delight to work on this project. We did test these and work with people who are blind and low vision to be able to make sure they made sense. And we did it to work with a community of people, but it ended up going viral. And it just really, I think, helped show that when you try to make something accessible for one group, you help make it accessible for many others. The Galactic Center was another one of the first pieces we did. This is the inner 400 light years of our Milky Way. And we're going to hear 3 different sounds in this composited piece. And by the way, we'll put up links later, but you can hear all of the individual solos, if you will, later. But just in the interest of time, we're going to hear the coolest energy material from Spitzer, the infrared in a soft piano. Then we'll hear the sort of mid-range material in optical / near infrared from the Hubble Space Telescope. That's like the plucky violin. And then the highest energy material is going to be in the xylophone sound. And as we get to the far right of the image where the supermassive black hole is, Sagittarius A star, that's kind of like where this crescendo of activity, it's like the downtown region of our Milky Way, and you'll hear a lot going on. So take it away.
Very cool. So you're actually working with a musician who's transposing the data to musical tones and into a musical space, not just a direct translation of frequencies into sounds.
Right. So we were taking into context the idea of here's all this high energy data and this supporting data. What techniques do we need to use to tell the science of the story? We wanted to keep it accurate, but also still make it beautiful, right? Right. We wanted to create something that people would hopefully want to do. So there are a few different, right? I mean, otherwise, why bother, I guess, if there's not going to be anyone who wants to tune in.
Right.
But we have definitely been experimenting with different sounds, whether it's sized or whether musical instrument based, or whether it's even like almost like a choral sound based on like the data helps tell that story. The data sort of drives you to select one or the other. It really is trying to represent it in a way that is not only correct, but also lovely, hopefully lovely.
Yeah.
So obviously it's subjective.
I think that's so interesting too, because I mean, since I also have visualization in my title, I'm sure this happens to you. Like people will just ask, well, what's the like the visualization tool, right? I just take data and I drop it in and I get a visualization out. And it doesn't happen. It requires making choices and being very intentional about how you bring these elements together. And so it's kind of interesting to think about that in sonification terms as well.
100%. Yeah. These two areas of visualization or really representation mirror each other, right? Just like the images are not space selfies or it's just points and click.
Right.
It's the same thing. These are not space recordings of just, hit record and here you go. This is a translation of information into something that can be heard. And the point of doing that is to be able to express your data in a different way. For us, there was definitely a point of accessibility, but also there is so much exciting science coming out of sonification as far as on the research side, because humans have developed a great sense of hearing over the eons, right? And we learn different things when we can engage different senses. Sometimes our sense of hearing is better suited to understanding things like variable stars or all of those, changes that can happen versus just looking at spectral data, right? Yeah, there's so many reasons to try these things, but I have to say it's an awful lot of fun.
Well, very good. Well, I guess we'll kind of end where we started with the beautiful Hubble image of M16. We'll bring it back home.
Bring it home, quite literally. This one's much closer. Go ahead, press play. So you can really hear the distinct X-ray sounds, which are those little high-pitched bloops, and that sort of sweeping drone across the more diffuse emission from the Hubble Space Telescope. And the differentiation between the two is important to be able to hear and frame. But it does make for something that sounds a little bit on the weird side. It was a very popular piece on NASA's SoundCloud for Halloween because it was like, scary sounds. And we had to keep saying this is not actually what the universe is trying to scare us.
Yeah.
Yeah.
Well, you use a little more theremin and you'd be good to go, right?
Yeah. Exactly.
Well, yeah, I mean, if we have any other questions, please feel free to put them in chat, and we can try to answer them live.
Great question from Corey. Did anyone or anything inspire you to pursue this work specific to the 3D work or the data sonification or both? I guess I'll just kind of try to answer all of the above. It's just, what I think it is in my job so far, I've had a very supportive manager who lets me have a little flexibility to play, not in an irresponsible way, but to sort of pursue things intellectually that might not necessarily pay off at the end. And I am just constantly excited by what colleagues around the world are doing and absorb all of that like a sponge and try to figure out how we can use some of that to make some really interesting creations. And yeah, I really credit being in a work environment that allows that creativity and that like drive of curiosity to be able to have the time to experiment with these projects. Because I'll tell you, every time it's paid off in these weird ways that we just didn't expect. We have a whole program now of 3D prints that we work with various groups of people around the US and around the world. And the data sonification really took me by surprise as to the response to it. It was like an emotional response for a lot of people. I think especially having come out during the pandemic, it was just a lovely distraction, a lovely thing to be able to think about. And yeah, I'm really happy to be able to provide that type of escape if that's what people need. So it's just been a great combination of having very talented people around me, time to sort of play, and then just putting it all together into something that turned out to be useful.
Well, I should ask, actually, with the 3D prints, are there 3D models if people have a printer that they can just download and be able to print?
Yes. The benefit of being a government-supported person is that everything I do is public domain. Awesome. So everything my team works on, we always really work hard to make sure it's usable in some way. So if you go to, we'll pop up the URL, but if it's chandra.si.edu/3D print, and all of the 3D models that we've worked on with our collaborators so far are up there, and all of the STL files are available. Plus we have some OBJ files. If you have different kinds of 3D printers, you too can hold a Death Star in your hand.
Excellent. Well, I don't see any other questions coming through. So thank you very much for sharing all of these great ideas today, and to kind of share these different perspectives and ways of being able to appreciate these amazing astronomical discoveries. So,
well, it's my pleasure. It's always fun talking with you, Ryan. So we should do this more often. It was great.
Exactly. Yeah. All right. Well, thanks very much. Thanks for everyone for tuning in. If you've been tuning in on Facebook, take a look at the OpenSpace YouTube channel, and also look at the OpenSpace project. If you're looking at OpenSpace, please check out the Morrison Planetarium Facebook page for more astronomy goodness. And thanks again. Thank you, Kim. Thanks for watching.